Okay, so today we're going to start something that we're going to do for at least a week, which is called related rates. We've done implicit differentiation already. Well, we've done plain old derivatives, taking the derivative of x squared, 2x. And we didn't have to do anything else, just that. But then all of a sudden we started doing implicit differentiation, where we had to add a y prime on the end of that. And if you remember, y prime is the same thing as dy over dx. Because now all of a sudden x wasn't your variable, it was y. And that indicated that you were working with something else. All related rates problems deal with one simple thing, and that is time. How do things change with time? We're going to start with one that's not very, well, hold on, let's do this. Okay, we're going to do related rates. I'm going to show you a 9-step approach. So, Bonnie, you've done this already, right? How was it?
Not a fun time.
Okay.
I mean, it's not that bad.
Don't sugarcoat it. It's okay.
It's just because each problem is different. So I would say it's hard to get like the diagram down, and once you have the derivative, you're fine from there. If you can come up with the equation, you're fine.
Wow, that was beautiful. I should have had you come to 6th grade and talk some people off the ledge. I've broken it down into a fairly algorithmic approach. Do you know what that means? Step by step. In fact, 9 steps that'll help you solve these problems. As you get more into these problems, you'll start to realize maybe I don't need all 9 steps. You'll get all fancies in your panties, and maybe you can do it in only 6. But initially, if you stay with the 9 steps, you'll be fine. Okay? And then, of course, you should always be able to enjoy spicy foods. Right? You all good on that one? Anybody not eat spicy foods? Not at all? Don't like spicy food at all? Okay, so, as I said, we've done dy dx already, but now we're going to start doing it with respect to time. So when you take the derivative, and we're going to start with this boring one, and it's boring because it doesn't tie into any real world problems. Almost every other one we're going to do has to do with something in the real world, like cars crashing into each other, people falling off of ladders, what other ones do I have? Leaky buckets, filling containers, that kind of stuff. So for instance, when we're done with this stuff, you'll be able to do the following. Summertime comes along, you go to Walmart, you get the kiddie pool for the backyard, because you want to lay out a tan in the kiddie pool. You put the hose in the pool to fill it up, but then you have to go do something. You'll be able to calculate exactly when that pool will be full. So you don't have to sit there and watch it. And it's easy. You just measure the flow rate of the hose and the volume of the pool, do some math, and boom, you're done. So I'm sure that's how you all do it. No? You would just look out the window and see if it's full yet?
Yeah.
No. All right. I mean, if that's how you want to do it, that's not how I would do it. All right. That kind of makes all the fun out of it, doesn't it? All right, so here we go. We want to take the derivative of this thing, and we're doing a derivative now with respect to time. So if I take the derivative of y, let's suppose we were doing implicit from yesterday. What would be the derivative of y? Y prime, good. The derivative of y is 1, but you took a derivative with respect to x, so you need a y prime, which remember is dy dx. However, now we're doing a derivative with respect to time, so you would get 1 dy dt. Follow that? What's the derivative of x squared then?
2x dy dt.
Not dy dt.
Dx.
Dx dt, good. And what's the derivative of 3? 0, because it's a constant. Okay, so we get something like that. We're going to take the derivative of both sides with respect to time, and we did the left side already. We also did the right side, and we get down to that. And I kind of skipped over that sentence. It says, fine, I'll come back to that in a second. That last equation at the bottom has how many unknowns? No.
3.
There are 3 there. dy dt, x, and dx dt. Simple rule of algebra, I need to know 2 of the 3. If I have 6 unknowns, I need to know 5 of the 6. Now we go back to that line that says find dy dt when x equals 1 and dx dt equals 2. So then I can plug in for x, I can plug in for dx dt, and solve for dy. And I get 4. Again, not exciting. Boring. That's commonly called a naked related rates problem because it doesn't apply to anything in the real world. We want to do some more interesting real world type things. Like, for instance, inflating a balloon. So let's calculate some stuff about a balloon. When you're doing related rates problems, it's common for geometry formulas to show up. Like, for instance, does anybody remember the volume of a cone? I know some of you had an outstanding geometry teacher, and you probably remember that. You just don't want to make everybody else look bad. Anybody?
Is it 1/3?
Yeah, it's
1/3.
Pi r cubed.
No. Okay, let's try something different. How about the volume of a sphere?
4/3 pi.
Alrighty. Alright, hold on. Let's try something different. How about the area of a triangle? Oh.
No, I don't think it.
Area of a square? Base time. Okay, area of a circle, which is a lie because pi r round, cake r square.
Oh.
That was good.
You just don't understand.
Oh.
Okay, here's the good news. You don't need to know any of those volume formulas. They'll give them to you. I'll give them to you. The AP will give them to you. You do need to know basic stuff like finding the area of a triangle, finding the area of a square, the other stuff that you already know. But volumes, you're good to go. So you probably don't remember that the volume of a sphere is, oh wait, let's do this first. We'll get to the sphere in a second. I forgot. You need to know the 9-step approach before we use the 9-step approach. I'm really good at my job. Number 1, draw a picture. Make it look pretty. And label that picture with anything that you know. By the way, many of these 9 steps will become more apparent as we start working through problems. Number 2, define the variables. A lot of times in the problem, you'll be able to use whatever variables you want. Some of them will be obvious. The first problem we deal with is inflating a balloon. Okay, so most people would choose R to represent the radius. If you don't want to use R, don't use R. You want to use the letters of your name, go ahead. Just make sure you tell the reader, or the grader, or whoever, what those letters represent. Number 3, what do we know and what are we looking for? What's the given information and what's the question asking? Number 4, write a general equation. That's probably the hardest part. But early on, you'll see it's really not that bad. The stuff in red is really important. Do not plug and chug yet. We'll do that later. And again, this will make more sense when we start working through some problems. Number 5, take the derivative. That's usually not too bad. The derivatives for related rates are nowhere near as nasty as some of the derivatives you've been doing already using implicit. Step 6, look at the snapshot. Okay, that's the exact moment in time we're talking about. Okay, so for instance, the first problem we're going to do, like I said already, is inflating a balloon. Well, that balloon inflates for a long period of time. What period of time are you talking about? In the example, I think, if I remember correctly, it's when the radius is equal to 2. Step 7, solve. Plug in what you know, solve for what you don't know. Excuse me. Step 8, does your answer make any sense? Many of you will skip this step, and I would plead for you to not skip this step. For instance, you're solving for the speed of a car, whatever the problem is. Ask yourself a simple question. Does that answer make sense? If you solve that problem and you get 3,482 miles per hour, you probably did something wrong. Your car is not traveling at 5 times the speed of sound. I don't care what kind of car you drive. So again, take 2 seconds to ask yourself, and some of them you're not going to be able to answer. You're not going to have any clue whether or not it makes sense. And then step 9, don't forget units. You don't need units through the whole problem, but you do need units on your final answer. Is that person falling off the ladder at feet per second, at meters per hour? Okay, ready? The first example, I don't think is on your sheet. So find a spot, we're gonna inflate a balloon. There's a balloon. It's inflating. Air is being pumped into a spherical balloon, which means it's a sphere, at a rate of 4.5 cubic feet per minute. Christian, what do you want to use for variables here?
J and C.
Okay, J represents,
The change of the radius.
how about just the radius?
Okay.
Okay, and what was the other one, C?
Yeah.
And C stands for, what,
The air that's being pumped in.
also known as volume. Okay, so you want to use C for volume and J for radius.
Sure.
You don't want to use B and R?
I just picked 2 random letters and
Those were random?
yeah.
Yeah, your name just happens to start with a C, and you chose C. Where did J come from?
My sister's name happens to start with a J.
There we go. Now the mystery unravels. I'm not using J and C. You can if you want, but I already have my slideshow done.
Okay.
There's my picture, it's a sphere, pretend. I know it's a circle, I teach geometry. I didn't add the 3D stuff on it. Step 2, I'm going to use V and R. Never should have asked you that question, it's my fault. Okay, so let's go back to this. What do I know? What's the 4.5 represent?
The rate.
The rate of what? The rate of the volume or the rate of the radius?
Volume.
Volume, right. Also known as dV/dt. So we know dV/dt is 4.5. What are we looking for?
dr/dt.
dr/dt, very good. And we're going to look for that when r is equal to 2. Let me get caught up here. Okay, so that's what we're looking for. And that's what we know. dV/dt is 4.5, dr/dt is question mark, but we want to find that value when the radius is 2. Step 4 is a general equation. And again, with this, you don't need to memorize the volume of a sphere. They'll give it to you. Okay, your turn. Take the derivative of that equation with respect to time. I'll get you started. What's the derivative of V? Very good, dV/dt. You do the right side. Some of you might be surprised by the answer. Elliot, you get it?
No, not yet.
What's the derivative of r cubed?
3dr dt. No.
Close, yeah. What's squared?
The dr dt.
No,
No, the 3.
no.
No, the r.
The r,
Yeah.
right. The derivative of r cubed is bring the exponent down, reduce it by 1, 3r squared. But since you took a derivative with respect to time, you need a dr dt on there. And then the 4/3 pi is just a constant, so that floats out in front. Which comes down to that. What is surprising about that formula? Anybody? Especially someone that did well in geometry. What's 4 pi r squared? Close? What's that? Close. It's the surface area of a sphere. If you take the volume of a sphere and you take the derivative, you get the surface area. What happens if you take the derivative of the surface area? No, nothing exciting. You're getting it. JJ, how many unknowns in that equation?
1,
Nope.
3. Well, we know dv over dt.
Yeah, but forget about what we know. Just
Oh,
looking,
then-
if you just walked in the room and saw that equation up there, I know you'd be really excited, but how many variable, or how many unknowns would you see?
3.
3, good. What are they?
dv over dt,
That's 1,
r,
2,
and then dr over dt.
outstanding. So if we're gonna be able to solve this puppy, we need to know at least 2 of those 3, which I think we do, yes? We know dv dt, we know r, and that gets us to that. And this is a snapshot, meaning that exact moment in time. And that exact moment in time is when the radius equals 2. And I'm going to assume that you could all solve that problem. Just for giggles, get out your calculators and tell me what dr dt equals. I have a feeling some of you may make the same mistake. So let's make sure you don't make that mistake. By the way, before you finish, when we stop calculating, will your answer be positive or negative? Positive, because it's getting bigger. Very good. Go ahead. Okay, I'm guessing you got one of 2 answers. You either got 0.884 or 0.089, oh, that would be 0.090. Which one? You should have gotten the second one.
Let's go.
If you got the other one, you got the other one by doing 4.5 divided by 16 pi, correct? 2 squared is 4 times 4 is 16 divided by 16 pi. You need to put that in parentheses. So the answer is 0.09. The problem is, with step 8, I have no idea if that's a reasonable answer. It's positive, so that makes me happy. What about units? units on that?
Feet per minute.
Are you sure? Okay, so here's a surefire way to get units. You can't screw this up once I show this to you. Notice that this 0.09 is equal to dr dt, right? What are the units on r? Is it feet? I don't remember the problem. It's feet. What are the units of time? Minutes. Feet per minute. Done. Okay. So this guy that you're solving for will tell you what your unit should be. Feet per minute. Feet per minute. If you were solving for dv dt, you'd need to know the units of the volume, you'd need to know the units of the time. And so instead of trying to figure that out the hard way, just look at back what you're solving for and you can get that answer. Okay. This is fun, right?
Super.
Good. Let's skip the next one and go to the ladder problem, which I think is the, flip it over, back page. This guy. Because this one's a little bit easier, so before we dive into that big, ugly, nasty one. Dun, 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 dun. Here, nope, not that one. There we go, this one. Woohoo! There's my picture. I chose to use X and Y, not J and C. Does everybody understand why I chose X and Y? X is horizontal, Y is vertical. I put the 20 in there. The only reason I put the 20 in there is because that's a value that doesn't change at any point during the problem. That ladder is always going to be 20 feet long. If it's a constant, you can put it in right away. If it ever changes, it can't be subbed in early. Okay, so step one, there's my picture. Step two was define variables. Okay, what do you want to call, how do you want to define X? David?
Horizontal.
Horizontal distance. Is everybody good with that? Horizontal distance. And then Y would be vertical distance. Makes perfect sense. Okay, no other variables there, so we're good to go. Step three, what do I know? What am I solving for? Okay, so 20-foot ladder I already have incorporated. If the bottom of the ladder slides away from the building horizontally at a rate of 2 feet per second, what is that 2 feet per second? dx dt. Is that value positive or negative? Positive, because it's getting bigger. 2 feet per second. Excuse me. What am I looking for? dy dt. dy dt equals question mark when y equals 12. Good. That's a 12. That's a 2, I mean. Pitiful. There we go. What's my general equation here?
Y squared plus x squared equals 20 squared.
Also known as
Pythagorean theorem.
Pythagorean theorem. Pythagorean theorem is a very common type of problem in related rates. What are we on, 5? Yeah, take the derivative. Ryan, what's the derivative of x squared?
2x dx dt.
Well done. Armin, what's the derivative of y squared?
2y dy dt.
Well done. And last but not least, Maggie, what's the derivative of 20 squared? 0. Good. Doesn't matter how long the ladder is. Does this problem seem silly? Doesn't it seem like if the bottom of the ladder is going out at 2 feet per second, that the top would be coming down at 2 feet per second? I think that's what your average schlub on the street would assume. We'll find out that that's not the case. How many unknowns in that equation? 4. Do we know 3 of the 4? No. Uh-oh. I know y. I know dx dt. I need x. How am I going to get x?
Another equation.
Don't even need another. I got an equation already. We're going to do something called a sidebar. We're going to come over here and solve a problem. Sidebar. You know what a sidebar is? You ever watch legal dramas where the judge calls the lawyers over for a sidebar? That's what this is. Okay. X squared plus 12 squared equals 20 squared. At that snapshot in time, I know that y is 12 feet, the ladder is still 20 feet, and I'm solving for x. Okay, how big's x? Everything was going along dreamily until they hit the Pythagorean theorem. What is it? 16. Hot diggity. All right. Bring this up here. All right. So, you know what? Are you okay with that? Divide everything by 2. Goes away. Fine. X is 16. dx dt is 2. Plus y is 12. And dy dt is what we're looking for, and that equals 0. So it's 32, and then divided by, so dy dt is equal to 32 divided by 12 would be 22 divided by 12 is 24, 2.667?
Yep.
Yeah? 2.667. I made a mistake. What is it? Why is it negative? Well, 2 reasons it's negative. Number 1, it's just the math. I didn't, I subtract 32 from both sides. Why should the value be negative?
It's going down.
It's going down, correct. Does that answer make sense? Oh, it's going down. That's good. It's negative. It's a reasonable rate compared to what we started with. If you got like 426, you're probably falling way too fast. And notice that you're falling faster than the bottom of the ladder is sliding out, which is fairly disturbing. What are my units?
Feet per second.
Beautiful. Feet per second. Done. Okay. Think you can do that? You will with some practice. Okay, let's ramp it up a little bit. And we'll go back to this guy. So we have an inverted conical right circular cone that's being filled with water. It's 12 feet high, 12 feet high, 6 feet radius. And then we've got some other information that we'll get to in a second. At some point in time, I've got a quantity of water in that tank. I don't know how high it is, so I called the height H, I called the radius R. Notice I learned I didn't ask what variables you wanted to use. So. The problem is giving you a flow rate of 10 gallons per minute, but nowhere in the problem are we dealing with gallons. So there's also a conversion there that converts gallons to cubic feet. 1 gallon is 0.1337 cubic feet. That's not something you need to memorize. If you need to do the conversion in the problem, it'll be given to you. Okay, so there's my picture. There are my variables. Oh wait, I have another variable. Wouldn't volume be another variable? Yeah, I forgot to list volume. V for volume. What do I know? I know dV dt, and I did the conversion now, so I don't have to do it later. I converted 10 gallons per minute to 1.337 cubic feet per minute. I'm hoping you can handle that, because you learned how to use Gazinta bars in chemistry, right?
Yes.
Good. I'm solving for dH dt. When? When the height is 3. How fast is the water level rising when the height is 3? If you were filling your kiddie pool in the backyard, it probably wouldn't be an inverted cone. It would probably be an inverted, well, not an inverted, it'd be a cylinder. Aren't most kiddie pools round? This is the audience participation part of the program. Thank you. Sometimes they're rectangular. I don't know if we got this answered before. Does anybody know the volume of a cone? No? That's okay. I'm going to give it to you. There's the volume of a cone. 1/3 pi r squared h. You might know it as 1/3 base times height. But it's a cone, so the base is a circle, pi r squared. Okay, this is a big problem. The big problem is I've got r's and h's on the right-hand side. That's bad. There's two ways you can handle this problem. I'm going to show you the way that I like better first. Then I'll show you the other method just so you can be exposed to it. But I don't think it'll take much for me to convince you that the first method is easier. There is a way that I can eliminate one of those variables. The question is, which one do I want to get rid of? R or H? Why R?
Because you have h, well, you need to find when h is 3, or you find dH dt when h is 3.
Couldn't have said it better myself. Well done. If I can get rid of that R and just work with H, I'll be happy as can be. In order to do that, we have to do some geometry. And you love geometry, don't you? Don't you?
Yes.
Good. Look familiar? What are they? Similar triangles. You got it. Everybody knows, everybody loves them. Michelle, what equation would you get from that similar triangle picture?
R equals 6 and H equals 12.
Close. Just one equation. How do you relate all those together? No? Ashley, help her out.
Isn't R over 6 is equal to H over 12?
Perfect. Now, there's a couple different ways you can do it. She said R over 6 equals H over 12. The radius of the water over the radius of the cone equals the height of the water over the height of the cone. You could also do 6 over 12 is equal to R over H. You could do H over R equals 12 over 6. You can do a lot of different ways as long as they correspond correctly. R over R, H over H. R over H, radius over height. I chose to do that one. Is that what you said? No, you said R over 6.
Yeah.
Same thing though. Cross multiply, solve. And as Luke mentioned, we want to get rid of R, so I solve for R. Which means I can take that puppy and put it into the other equation above it and get rid of the R's. Which would give me that. And it is much easier, much easier to do this before you take the derivative than after. Especially when you see how nicely this simplifies. It simplifies down to that. Easy. Lovely. Simple. What's the derivative?
Pi over 4h squared times dh dt.
Say that once more.
Pi over 4h squared times dh dt.
Beautiful. What's the left-hand side?
dv dt.
Uh-huh. Is everybody good? That's 3 pi over 12, which we simplified to pi over 4 because they're equal. How many unknowns? 3. Do I know 2 of the 3?
Yes.
You bet I do. I know dv dt and I know h. Before we continue, will dh dt be positive or negative?
Positive.
Positive, because the tank is filling. The height is getting bigger. Therefore, the rate of change is positive. All the hard stuff's done. Now the easy stuff, just blood and chug. Boom. Solve it. Boom. Answer. Boom. Units. Boom. Does that answer make any sense? Well, I don't know. It's positive. Sure. Let's go. So if you think about this, you solve your kiddie pool problem, you know the dH/dt, how fast is the height of the water changing over time, and if you know the height of the kiddie pool, then you know it's 0.189 feet per minute, and my kiddie pool is 2 feet deep. Do some simple math, and you know that you got X number of hours before you have to get out there to shut the water off so it doesn't overflow all over the yard. Or you could just look out the window and see when it's getting close. Okay. Okay, so here's the second approach. You're not going to like this, but I'll show you anyways because I don't want to deprive you of a learning opportunity. If I go back to the original problem, I have 2 variables, which means I need to take the derivative using product rule, which gives me that. Okay, derivative of the first times the derivative, first times the derivative of the second plus the second times derivative of the first. In that equation, there are 1, 2, 3, 4, 5, 6, 5. 1, 2, 3, 4, 5 unknowns. Now I need to find 4 of those 5. I don't have 4 of those 5. So then I got to go back to the similar triangles again, okay, which is this guy. And then I got to take the derivative of that similar triangle and I get this guy. Now I can solve for dr dt, which gives me this, and then I plug it back in and it's a mess. Okay, how about we stay with the first approach? Good. We're going to stop there. I don't think we want to do that yet. We'll save that for Tuesday. So, over the weekend, or tonight, or whatever, you have 2 problems. They are test prep questions, which means they're not in the electronic